Assalamualaikum warahmatullahi. Salam sejahtera. Good morning, good afternoon. Uh, this is to discuss the solution for the tutorial 2 on the shear stress, which I have given the questions early on. So let's start with question number 1. In this question number 1, uh, it shows that figure 2.1 below shows a basic punching press where a hole is expected to be punched out of a plate having a shear strength of 275.8 megapascal. The compressive strength of the punch is limited to 345 megapascal. First, compute the maximum thickness of the plate in which a hole of 63.5 mm can be punched. Second, if the plate is 6.35 mm thick, determine the diameter of the smallest hole that can be punched. Okay, so here we have a basic punch press where you have a puncher, right? And then you have a plate. This is the plate, and the plate has a thickness T. So there's a plate of thickness T and a puncher of a certain diameter D. So we have two objects or two components here, the plate and the puncher. And then they give us the plate have a shear strength of 200. This plate have a shear strength of 275.8 megapascal. And then the punch is also limited by the compressive strength. Okay, and it is 345 megapascal. So here on, we need to understand what kind of failures that we try to avoid. Because of the shear strength of the plate, the puncher will try to push the plate through this hole. There is a die here, okay, and that die with the punch, the puncher and the die here will create shear at the plate, and this plate will come out as a blank like this. And here is the thickness of the plate. Sorry. And then you've got the shear stress around the peripheral of the plate here. Okay, so the area that being punched out is pi d, which is the circumference times the thickness of the plate, sama ukulilit kali tebal of the plate. And given the material of the plate, is given 275.8 megapascals. So this thing will fail by shear, and the puncher is also limited by the compressive strength, which is 345 megapascal. I've drawn the free body diagram of the puncher here, and it is less than 345 megapascal. So you can see that the puncher will fail by compression and the plate will fail by shear strength. So we've given the two criteria, tau max, which is just shear strength of the plate, and compression strength, sigma max. And so based on these two criteria, we have to make decisions that we have to comply with both criteria. So when we want to do punching, the tau max must be bigger than the allowable shear stress. And in order to prevent the failure for the failure of the punch, we must make sure that the stress is less than the allowable compression strength. So we have puncher strengths. I'm going to look at puncher strength here. So this is the free body diagram. So the stress is P divided by the area there. So P max, the puncher strength, the force that can be sustained, daya yang boleh ditahan oleh puncher is P max equal to sigma A. Sigma A is given by 345 Newton per megapascal. This is given here. And then the area is given by 63.5 pi d square over 4. And we have the stress or the force from the puncture is expected to be 1.809 times 10 to the power of 6 Newton. So about 1.09 meganewton. So we check with the plate shear strength, and we find that the tau max, the shear stress of the max, equals to V divided by A. V is the shear force. In this case, V equals to P. And then we know that tau max equals to 275.8 megapascal. This is the stress that we need to overcome in order to push the plate through. So equals to P 1.095 divided by A. A is pi dt. Pi 60.5 diameter and T is the thickness. So from this, we can calculate what T is. T equals to 19.8 millimeter. The second question asks us, what happens if our thickness of the plate is 6.35 mm? Okay, what is the smallest hole that can be punched through the plate? Now, it is given this value, and we need to find what is the smallest hole. As we increase or we make the hole smaller, we also need to make the punch diameter smaller. When the punch diameter is smaller, the stress of the punch will go up. So here we check for the stress of the punch. So first we have to calculate what is the force needed to push a blank of T equals to 6.35 mm. So I have here 275 megapascal, which is the shear strength of the plate, equals to P, this is the shear stress, P divided by pi dt. So pi dt is given 6.35, and this is one equation. The second equation is the maximum stress that can be sustained by the punch is 345 megapascal or Newton per millimeter square, and this is equivalent to P, force applied, divided by the area of the punch. So the area of the punch is pi d square over 4. And we equate these two things, and P equals to 275 times pi d times 6.35 equals to P 345 times pi d square over 4. And from there, you will get your first solution, which is 20.25 or 20.3 mm. That's the diameter of the punch that can be used to punch through the smallest hole here. So the smallest hole is 20.25 mm. So what happens if we want to punch a smaller hole than this? Well, you have to use a stronger punch material. So now the strength is given by 345. You might have to use a of different material. So that is the solution for question number 1. So this question is trying to make you think, how do you obey two conditions? First is the compressive strength, second is the shear strength. And that is perhaps the overall thinking skill that is required from you. So we move on to the next question. So we have a double lap joint here, double shear joint. So I draw the free body diagram, 400 kilonewton, which is equals to P, and this is the resistant force at the bottom and top surface. So that has got to be P over 2, right? So that is the formula for double shear. If it's a single shear, it will be just P. So we take one surface, and then P equals to 400 divided by 2 for this surface. So it is 200 kilonewton. So tau max equals to, given to us, 300 Newton per millimeter square. This is equals to 200, tau max is 200 kilonewton is this force divided by the area. So pi d square over 4, and therefore we can calculate the minimum smallest bolt is 200 kilonewton divided by the area, pi d square over 4, pi over 4, and then 300 Newton goes here, find the square root, and you can find that D equals to 29.13 millimeter. This is quite a straightforward question that you can use in your study. So there's not much to be discussed. The only things that you need to remember, this is where failure occur. So the first skill that you need to do is identify whether this is a single shear or a double shear problem. Yeah? So similarly before this, it is a single shear problem. This is a double shear problem for question number 2. I think we can move on to question number 3. Is there anything else that we can add to here? So maybe I should put this here as P over 2. That would help you to better understand. Okay, so let's move on to the next one. So question number 3. Question number 3 is a 200 mm diameter pulley. So we have a pulley of 200 mm is prevented from rotating relative to the 60 mm diameter shaft. So you have a 60 mm diameter shaft by a 70 millimeter long key. So at the key, there is a key 70 millimeter long as shown in the figure below. If a torque T equals to 2.2 kilonewton meter is applied to the shaft, so this shaft is undergoing a torque of 2.2 kilonewton meter, determine the width B, B lebar dia, this is given B, this one is B, okay. Determine the width B if the allowable shearing stress in the key is 60 megapascal. So this is about shear stress. So this question is asking you to find the width needed to prevent this pin from failing by shear. So I draw a line, a red line here to show that this thing will fail by shear. Okay, and the shear stress or the area for the shear stress is equals to B times 70, and the force from the shearing stress equals to the stress, shear stress times the area, we get the force. What is the distance of this shear stress from the origin, from the axis of the rotation, from O? It is given by this radius or jejari, which is half of the diameter. So diameter is given by 60 over 2 equals to 30 mm. Okay, so I got this radius here, 30 millimeter. So the shear stress, this is a single shear. So the shear stress from the force F equals to tau equals F divided by A, and that must be less. A equals to 70, lebar panjang dia 70, lebar is B, 70B. This must be less than 60 megapascal. And you have to remember there is a second equation that you have to look for, which is the torque. Torque is force times area. Now, how do I know that force is here? I must put the force somewhere. So I think from my understanding of shear force, the shear stress, the shear force is resulting from the shear stress of a distance of this. So equals to Fr. So I said here torque T equals to Fr. I know the torque is 2.2 times 10 to the power of 3 Newton meter. My radius is given 30 mm here. So I change that to 0.03 meter, and I get here 73.33 times 10 to the power of 3 Newton. When I combine these two equations, yeah, and I can calculate that B must be larger than 73.3 kilonewton divided by 70 times 60, and I can get my minimum B of 17.46 mm. So it's a single shear problem, obeying the condition for the torque, and I know what my shear stress is, 60 megapascal. Yeah, so perhaps the student has to have the knowledge that they have to understand that shear stress is due to the failure of the key. The key will fail, and what is the width that I must prevent the shear strength from becoming larger than 60 megapascal, or the shear stress larger than 60 megapascal. So that's, I put that fail by shear here. All right. So that's question number 3. So we move on to the next question. Question number 4. Compute the shearing stress in the pin at B for the members supported as shown in figure 2.5 below. The pin diameter is 20 mm. So you have a bracket here, right? A, B, C. That bracket is subjected to a force of 40 kilonewton at an angle of 35 degrees from the horizon, so at point A. And there is also a ball resisting the movement of C. So this ball is providing us with the vertical reaction force. There is a pin at B. The pin will resist both the horizontal force and the vertical force. So the length from A to B is given 200 mm. The length from B to C is given at 250 mm. And the pin at B is constructed such a way that we have a double shear. So remember, we get a double shear here. So maybe I can write it here. It is a double shear. So I'm going to write here. Double shear. Is it important? Yes, it is important because later on we will make decision based on this double shear issue. So from this, I draw the free body diagram, 40 kilonewton, angle 35 degrees. I made a pin at the FBX, FBY, and there is a reaction force at point C, CY. So then I can calculate the summation of moment at point B equals to 0. I'm taking it clockwise to be positive. So 40 kilonewton cos 35 is the horizontal force times the distance here, AB, given 200 mm. So it is 200 mm here. And there is also a counterclockwise moment from CY, so negative CY, times the distance here, 250 mm. This is equal to 0. And I can find CY equal to 26.21 kilonewton. Okay? And from there, I started to use the force equilibrium equation. So summation of force in the vertical direction, Fy equals to 0. So Fy kita ada, there are 3 forces here. Fby, Cy, plus the force 40 sine 35, which is upwards. So then I can find that I know Cy is 26.21 kilonewton. So my Fy equals to minus 49.15 kilonewton. So this is acting downwards. I can, if I want, to put a arrow here. And then similarly, I can find using the force equation, force equilibrium, summation of force in the horizontal or x direction equals to 0. Fbx plus 40 cos 35, so I assume Fbx to the right here, plus 40 cos 35 degrees, which is memang to the right, equals to 0. There's no other force. So I can find that Fx equals to negative 32.77 kilonewton. So here is a case where my Fx is 32.77. If I want, I can label it to the left, but this is okay. So when you have force in the horizontal and vertical direction, you can combine them because this is a cylindrical pin. So you want to find what is the largest force acting, which is the resultant force at B. So you find the square root of Fx squared plus Fy squared equals to 32.77 Newton here, Fx, and Fy is 49.15, and finally you get 59.07 kilonewton. And again, we reminded ourselves that this is a double shear, so I need to reduce the force acting on the pin. It is not 59, but P over 2. So tau equals to shear stress acting on the surface divided by A, and we know that the shear stress is because of double shear, it becomes half of the pin force. So P over 2 divided by A, P divided by 2A. So P is known 59.07 kilonewton. This is a 2. A is pi over 4. And then D is given here 20 millimeter. So pi d squared over 4. And therefore we get this 94.01 megapascal. Okay, so that's the answer to the whole 4 questions. I would like to encourage you to try other questions available in the book or on the in YouTube or other website, and you can also go for printed materials to enforce your strength. This exercise may not be enough, and you have to work on your own to be independent so that you can understand the logic, and when you can develop some analytical skills when you are facing with shear stress problem in the strength of material. So thank you very much. I hope you benefit from the session, and please have a go, try to solve it on your own. Thank you. Assalamualaikum warahmatullahi wabarakatuh.